So as I was saying, we have, instead of 10 NC field equations, we'll have 6 here. This 6 is due to the fact that we already have 4 relations here. And so that will be 10 minus 4, giving us 6 equations. So in essence, we will need another 4 equations that will make up for the 4 missing independent equations that we'll have solved for this independently, uniquely. And so as a result of that, we'll need also, just like the Lorentz gauge in classical electrodynamics, which is just one expression, which made up for the 1 missing equation from this as a result of this relation here. We are going to need 4 equations to make up for the 4 equations missing from this as a result of that. These 4 equations in NC field equations is provided by what we call the harmonic coordinate conditions, given by that. Here, of course, mu nu are contracted. In this case, we are left with lambda. But then again, lambda ranges from 0, 1, 2, 3. So those are 4 equations. And so this, in addition to these NC field equations, solves it uniquely and then also unambiguously determines whatever the metric tensor will be. And that will give us a complete set of equations. So that was the story I had to tell here. I don't like telling stories unless absolutely necessary. I might have missed 1 or 2 things or mixed some things up. I apologize for that in advance. And I hope that wouldn't in any way affect what we'll be doing next. So I encourage you, and at this point, again, I would like to say, just like I've always said, Wemba's book has been a very good inspiration and a very good resource all along this presentation. And I owe it to him personally. Well, I don't know if he will ever see this, but if he does, he should know that really he has given us a masterpiece. And I will encourage anyone who is seeing this right now to find time to look at his book. Right from the beginning to the end, I don't need to give specifics. I think the whole book itself is a good thing for any theorist or any physicist, especially a beginner. So he was able to write it down to that level where someone can really pick up. Okay. Moving on, I will simply say at this point, so we have just explained how we have some ambiguities in this and how all that have been obviated, and also we have avoided that by giving us some solutions. Okay, so we are going to look more closely into this freedom. So we can, like we have said, by this transformation, obtain a new G, which G prime mu nu, which might as well be substituted in this equation, and then again it will still satisfy the NC field equations. So we want to see how the metric tensor, of course we are going to be talking about the linearized theory here. So we want to see how this transforms and what other kind of freedom can be entailed or can be contained in H, especially since that is what we have here. So we want to see how that could be obtained in H. I think I might have missed 1 or 2 things here in this. This would be a very serious issue. Hopefully this wouldn't be an issue when that comes. This is, I believe this is lambda, and maybe obviously this should be lambda. Otherwise then we have a serious problem. It should be lambda. Okay, so let's move on. Now moving on, I think we might need the expressions here on top, so I'll leave them. Now at this expression, or even just this, so I'm going to be using the linearized theory. We are considering the fact that if there's any such transformation that changes x from x to x prime, which contains this expression in this very weak field, we are saying that we will also be able to obtain a new G. So linearizing all this now, for instance, we know that G prime mu nu, just as we showed yesterday, might as well be written as this minus H mu nu. And then again, of course, G lambda rho is the same thing as eta lambda rho minus H lambda rho. Yeah. So putting all this in this expression, so I'm going to put this by saying eta mu, okay, so this is prime, this should be prime, sorry. So this should be prime nu minus H prime mu nu equal to D the x here, this is the x lambda. Then here, this is f prime mu, so it will be the same as simply x mu plus here epsilon of x. Exactly, that's what we should get. And then moving on again, I have the x rho. I have here with me, what I've got here is x prime nu. So I'm expecting that this should be x nu plus here nu of x. And then of course multiplied by here g, okay, not g, eta lambda rho minus h lambda rho. And you can see that this of course follows directly from this. Okay, so we've substituted that, we've substituted that, we've substituted that, and also substituted that all. Okay, these transformations derived from here. We'll say that by this transformation, we can also obtain new g's in this case. Now we need to mention here that the Minkowski metric is an invariant, is the same, no matter what transformation you perform on it. Now this, of course, so I'm going to use a curly bracket. If I differentiate this, I get a chronicle delta mu lambda, and then this will be d here, mu of x, the x lambda. Okay, well, and that, and this will be multiplied by a chronicle delta nu rho, that's differentiating that, and then plus the nu of x, this will be the x rho, and then that, and then I have here lambda rho minus h lambda rho. This again is equal to, I open up this bracket, mu lambda nu rho plus this mu lambda, that nu x, the x rho, plus here nu rho epsilon mu of x, the x lambda, and then I have here plus multiplying those last terms. This will be epsilon of x, the x rho, and then of course this whole thing here is multiplied by eta lambda rho minus h lambda rho. Okay, I'm going to do something here. Okay, the very first thing here that I can do is say this multiplied through lambda here, nu rho. So I'm multiplying in this lambda rho plus mu lambda nu of x, the x rho, eta here, that should be lambda rho, plus nu rho, the epsilon of x, the x lambda, and this should be lambda rho, and then plus here. Okay, I think I shouldn't waste my time doing this. Okay, I've stated here from the beginning that derivative of this with respect to x nu is of order h, Now I have that excuse me, occurring twice. So this is of order h squared, and of course, you know from our last presentation that should be 0. So I'm not going to bother myself with that. So what it means on the last one, so I'm simply going to go straight with saying, but then it will take a minus. This will be minus of h lambda rho multiplied by chronicle deltas mu lambda, chronicle delta here nu rho. Fortunately for us, we don't have to deal with any more terms because this now is of order h. Multiplying with this again gives us of order h squared. So that would be 0. And this is already of order h. Multiplying with another h again, that will be of order h squared. That will be 0. So I'll simply just throw that out. Now here, the lambda changes from this chronicle delta to mu, and the rho changes to nu, minus, I'm bringing in this last term, the lambda changes to mu and the rho changes to nu. So this is going to change here to mu and nu. This here, okay, yeah, so I have a lambda here. This is going to be the eta nu, epsilon nu, sorry, this is the x rho. And then this will be eta, instead of lambda, I have a mu rho. And next will be plus the epsilon mu of x, and this should be the x lambda. Now instead of, okay, so I'm going to have a lambda, and then instead of the rho here, I'll have a nu. And by the way, remember that this whole thing is equal to, so here, eta prime mu nu minus h prime mu nu, right? Yeah, that's what it is. We said this is an invariant, so prime or not prime, these two are the same, being on different sides of the equality sign. I have a minus sign here, so I simply multiply the entire expression by minus, this is h prime mu nu. So what I have essentially is h mu nu minus here nu of x, the x rho, eta mu rho minus epsilon mu of x, the x lambda, eta lambda nu. And this is what I obtain as an expression here denoting this ambiguity. So, well, what I've got here in this case is all contravariant indices. I'm going to lower them now, both. Yeah, I'm guessing this is the same with what we had right here as we've written it out as one of the things we really wanted to show here. So this is equal to that. Now, when we lower it and we expect to obtain something like this, again, from the instant field equations, all we are saying is if h mu nu satisfies this equation, then some h mu nu prime defined by this transformation satisfies the same instant field equation. So again, from what we've explained here using the what you will have had for the exact instant field equation, we are seeing that now being expressed in its linearized form. This ambiguity that we have explained using this transformation, we are now seeing here now, instead of this transformation, we're having this. So with this again, this just again illustrates what ambiguity we have as a result of this coordinate transformation. And of course, the fact that the instant field equations is satisfied either by this and then again at the same time by h mu nu prime, which is defined by this transformation. The fact that both this and this satisfy this instant field equation is known as gauge invariance. Of course, again, you know that this is analogous to what we have in classical electrodynamics. Okay, enough of the story. So we have this to be equal to that. I'm moving on now. So my intention here is to lower this, so I'll simply write this on top, maybe as one of our expressions, important expressions here. H mu nu minus. Here, so let me put this up. Thanks. And this is mu rho minus. This is mu here of x. This is the x lambda, eta lambda nu. Okay, so we can box that up with the rest and erase what we have there. Now, at this point in time, I can decide to lower the two indices, mu and nu. And I'll simply use again what we know to be. Okay, so, yeah, good. I think this is a very good point for me to recall this yesterday. I made a statement saying that I think that was based on this. I had an expression, eta mu nu, h something like this lambda. And we showed that this, I believe, eta nu lambda h mu nu. Which has to do with this being directly moved to this side and that moved to that side. So very quickly, yesterday I made a statement saying that this is true, especially maybe because of the approximations we made on the metric tensor being just infinitesimally different from the metric tensor. That's yes, no, from the Minkowski metric, sorry, yeah. Infinitesimally different from the Minkowski metric. In other words, I was presupposing that this might not be true where this to be, okay, let me not use h, let me say some ordinary tensor, yeah, an exact tensor, nothing linearized in this case. In other words, I was saying that this might not be true if we were to consider something like that. So I'll just do something here and then we can decide for ourselves whether or not that is possible. Now looking at this expression here, which is what I've got to be. Okay, so I'm going to make some very serious assumptions there. Thinking here, so this is G mu nu lambda. This is of course the same thing as C lambda and mu. Okay, well, what I've done here is simply to kind of lower mu. I have no dummy indices anymore on this right hand side, just like I have here. But then again, I can decide to add them. If this time around what I decide to do is to lower lambda. If I'm lowering lambda, then this is going to be, for instance, the same thing as G, and then I'm going to have lambda definitely here. I can use rho this time if I like. T, this will be, well, I'm going to assume this is symmetric, so I won't bother myself of what order this two will be. Can you see that, of course, this whole thing is equal to that? But then again, on this side, I can change rho to nu. It's a dummy index, and I have the freedom to do that. So this is the same thing as here, lambda nu T nu mu. Again, okay, maybe we can attach the condition of symmetry on the exact tensor. So, but the metric tensor is always symmetric. But then you can see that this is the same thing as G nu lambda T, what is it? Is it mu nu? Again, since I'm assuming T to be symmetric. So you can see here that indeed this is true or the same with that. I think this should be, I made this statement in the last two presentations on gravitational waves, the basics. So in other words, this might as well be true again, even for the full metric tensor, and not just the linearized thing over there, the Minkowski metric. Well, that is just by the way. Let's move on, but it was good I made that statement. Inevitably, there might be one or two mistakes here and there, but I apologize again in advance for that. Hopefully there wouldn't be much, and it wouldn't be such as to cause any kind of misconception in anyone who is listening to these lectures. Okay, so lowering this two, I need to do that using eta, not G. So I'm going to say something like eta alpha mu, eta beta nu, so that this prime alpha beta. In other words, I've used this one to lower mu and this to lower nu. That is what I've got here on the left hand side. That again, of course, will be the same thing applicable here. I'm going to be lowering. Okay, I think to be able to do this, sorry, we'll still do the same thing. I think I would like to write this in a way that will make this method I'm using now quite easier. This is minus, let me say the rho, yeah, epsilon nu of x, eta mu that minus the lambda. Okay, well, I don't think it actually changes anything. Eta lambda nu. So what I had before, alpha mu beta nu, h prime alpha beta, then again alpha mu and then beta nu, h here again alpha beta, and then here I'm going to have again. So what am I trying to? I'm going to be consistent with my lowering. I'm using alpha to lower mu. So I'm going to have here with me alpha mu again alpha beta nu. In other words, rho here is unaffected, but the nu here, remember, was lowered using beta, so beta is what that becomes of x. And eta, then of course I'm lowering mu, so I'm going to leave rho up there. I lowered mu with alpha. So that's what I said, that's what I meant by being consistent. This will be minus, again, alpha mu, and then beta nu. So I just need to make the identification. Lambda here is unaffected. Mu have been lowered with alpha. And then eta, lambda will be left there untouched, has been lowered with beta. Okay. To make all things, simpler, if that is what we got, we can say that this is the same thing as mu nu, eta beta nu. I can have that prime alpha beta minus just the usual thing. This is that. And this is alpha. This will then be the lambda, alpha of x, lambda, beta, the entire thing is 0, and of course the usual thing, alpha, mu, none of this should be 0. We can't have it to 0. So if that is the case, then what we have in the bracket will be 0. So this will be that, beta, alpha beta, minus rho epsilon beta of x, eta rho alpha, minus lambda, alpha of x, lambda beta, and this is, okay, well, no, it can't be 0, we just made that equal to that. Well, yesterday we showed that, well, in our expression, that this is the same thing as the chronicle delta rho alpha. So we do expect, of course, this will be the same also here, lambda beta. So at this point, if we decide, then of course is what we can do next. Is the only thing we really can do next. Simply evaluate with the chronicle deltas prime, alpha beta. This then will be equal to h alpha beta minus here changing. So what else do we have here on this expression really? We've got rho here. We can change it to alpha. So this becomes the alpha epsilon beta of x. And here we have minus, the lambda becomes beta, beta epsilon of alpha of x. Yeah, in this last expression, I can decide to see if I can get something close to that. Make the first index mu and the second one nu. So on this expression, if I make alpha mu and beta nu, this will simply mean h prime mu nu equal to h mu nu minus, okay, so I have here the epsilon nu of x. This will become the x mu minus again the epsilon. I'm guessing the first one, this should be mu of x and the x of nu. And that gives us that, I believe. That is what it should be. Yeah, that is correct. Well, we've written this first, doesn't matter. It's still minus, both of them have minuses. Minus that, minus that. So I guess it's all the same. Yeah, it's all the same. So we have just been able to show this expression. And this is what we've got. And like we have said, that given this expression, for every h mu nu that satisfies this Einstein field equation, we can obtain a h prime mu nu that satisfies this Einstein field equation. And what is the condition we are working with here, or should we say what is the equation, set of equations making up for the missing equation as a result of the Bianchi identity? Well, this might as well, if you like, be contained in what we have also obtained here, the linearized Bianchi identity, which is an expression that you can see. So just analogous to the Bianchi identity here. This is the Bianchi identity for the left-hand side of the Einstein field equation, exact Einstein field equation written in this form. Now for the linearized Einstein field equation, like I said, I'm being careful in calling that the Bianchi identity, but well, you can see it does help us here because this is contracted, nu is contracted, but I have here lambda, which ranges from 0, 1, 2, 3, a set of 4 equations. And these equations is what is responsible for the 4th degree of freedom, which keeps this set of equations from being 10, or what, yes, exactly, from being the 10 Einstein field equations. So we have just 6. But now these 6 equations have been again made up to become 10 by the following set of equations here, which we have obtained as 4 coordinate conditions, which we have obtained from the harmonic coordinate conditions. Now, this expression here we are going to use to obtain, to illustrate that this equation here in its linearized form, this set of equation in its linearized form, in addition to this, will help us determine h mu nu uniquely. In other words, we can also solve for h mu nu uniquely in the same way that we solve for A alpha here uniquely in classical electrodynamics. So let's go ahead to do that very quickly. We have just obtained this expression. I think since we have it here, I don't need to repeat them all over again. So let's just wipe all this out. In this form, the harmonic conditions as given by this. This is G mu nu gamma lambda mu nu equal to 0. In its linearized form, I have here eta mu nu minus h mu nu, multiplied again by the linearized form of that, which I believe to be 1 over 2 eta from our last two presentations. It will be easy to see how this came about. And this is going to be plus h rho mu, comma nu minus h mu nu, comma rho. All this is equal to 0. Well, we are not going to bother ourselves with every term obtained with the multiplication of this. If we expand this, this will be h multiplying its derivative of h all through. All those will be order of h squared, and all that will be negligible. So what we have in essence here is 1 over 2 eta mu nu lambda rho multiplying h rho nu comma nu plus h rho nu comma nu minus h mu nu comma rho. This is all equal to 0. Well, we can multiply both sides by the 2, and that gives us just so we can do without that. So I have this lambda rho multiplying h this comma mu plus mu nu lambda rho multiplying this comma nu minus. Okay, so let me just say equal to mu nu lambda rho h mu nu comma rho. Yeah, and expanding this. Looking at this expression here, and we kind of have a lot of dummy indices. We have mu mu, we have nu nu, we have rho rho. The same thing here. So what I'm trying to do here is, I think I can interchange mu and nu here, and it will be the same with this. If I do that, so the usual thing, wherever I see nu, I put mu, wherever I see mu, I put nu. So this will become eta mu nu, of course symmetric, doesn't even matter the order. But the important thing for my own purpose is that this becomes that mu nu lambda rho h rho mu nu equal to that lambda rho and h mu nu comma rho, and this gives me 2 of that. So in other words, I can, in the usual way that we have been solving these problems, I don't think I need these 2 dummy indices or whatever that is. Well, let's see what that will look like. I can just for now combine these 2 first of all. I have 2 of them, mu nu, one step at a time, rho mu comma nu equal to that comma that. Yeah, if I do that, I don't want to mess with this derivative mu here. I may decide to raise this, but then again I can raise this. So this is the same thing as some mu nu 2 times eta lambda rho, this here minus here lambda rho h mu nu comma that. This is equal to 0. Okay, so if I have that, I think well, we have here to be the derivative respect to rho, this derivative respect to nu. So, well, what I'm trying to do at this point in time is, well, we can say this is not equal to 0, and what we necessarily have to be equal to 0 is whatever is left in the bracket. Okay, now at this point in time, we do have a situation here. First of all, we can raise this. I can leave this out, by the way. Yes, if I leave this out, my reason here is I do not want to mess with the derivative, what I'm differentiating with here. This is the x rho, the x nu, and this is the x rho. So in other words, we are looking here at a relationship which I believe must have been enumerated somewhere here. So I'm leaving what I'm differentiating here with respect to. So what I would like to do is actually write this to be equal to, this is that. Please know that it's all the same. It's just that I want something to be very convenient here for me. This is the same thing, but then mu nu. So you may be wondering why I'm choosing this over that. Of course, This is just the same thing as what I've written before. As you can see, all I've done is simply I've selected this to be the one outside the bracket. In essence, let me just go on again before I discard this one. This is the same thing as this. If I raise this, this will be row, but then new, comma new, minus. If I raise this, this will be for me some new. Well, you can say, for instance, that these two are contracting, and then so I have this, for instance, to be a scalar, just like we do when we contract Ricci tensor to obtain the Ricci scalar. Well, it's not a big deal, but then again, I representing it with new like this, sigma, anything, whatever. It's still the same thing. It's still a scalar, so we can just leave it as that. We can simply make the statement that this is not 0, which will imply, for instance, that h. And by the way, I raise this mu, and it becomes a nu. And if h is symmetric, I might as well write it again. I think we have illustrated or explained why this is possible. I might as well write it in this form, putting nu before rho in this order instead of that order. So this is the same thing as 1 all over 2 of h nu, but comma here, rho. I'm guessing that this expression here is the same with what I've got here. So I have a dummy index here, but I'm differentiating with guess one. The derivative is with respect to that dummy index. That's what I've got here, nu. And this index here, nu, is what we are differentiating the scalar in the right hand side with respect to. And so I have here this row, the scalar on the right hand side. That's what I'm differentiating it with respect to. So in other words, I've obtained here an expression which is satisfied by, if you like, h mu nu. That's what that is. Now the idea here is, this here is the condition that we've got here satisfied by h mu nu. And of course, as a result of this degree of freedom that we have in our Einstein field equation, the linearized Einstein field equation, as of course adumbrated by this coordinate transformation, we have here this coordinate transformation, which here is affected by the presence of this function, which should be about 4 of them actually, of course, because of the mu here, not contracted mu ranging from 0, 1 to 3. And so we can see that this expression here, we're just saying, of course, if this is the condition for h mu nu, then it might as well be the same condition for h mu nu prime. It should be, in other words, h mu nu prime should satisfy this relationship. So that indeed, since this h mu nu satisfies this relationship, then of course, since this satisfies the Einstein field equation, if we are saying that this satisfies the Einstein field equation, then this also should satisfy this. Let me take that again. If we say that this satisfies the Einstein field equation, and at the same time with this, and we have here shown by the additional set of equations, 4 of them linearized this time around. That's the linearized harmonic coordinate conditions. By the linearized harmonic coordinate conditions, we show that h actually satisfies this. Then this also should satisfy this, because you know, if it doesn't satisfy this, then it really doesn't make up, because first of all, this satisfies the Einstein field equations, which should have been 10 but are not 10 because of our Bianchi identity again. So let me call that Bianchi identity, as a result of the 4 degree of freedom created as a result of this Bianchi identity. So what did we say we had to do? We needed another set of equations to make it up to 10. So those set of equations were this, the harmonic coordinate conditions, in which in its linearized form implies this, which we have just shown to be done. So it means that h mu nu, apart from satisfying the Einstein field equation, has to satisfy this expression. In other words, if also by our coordinate transformation, and we are assuming that gauge invariance, like we have said, it therefore means that if this also satisfies the Einstein field equations, then h mu nu necessarily has to satisfy these two. In other words, let me just intimate that here. We should have something like this: h prime nu rho, comma, nu to be equal to 1 all over 2 h nu, comma, rho. Yes. In other words, we should have that. Okay, well, sorry, I should have a prime. Really, that's what. I should have a prime here. I should have a prime, and that is that. Okay, in order to be able to show this, I will need my H to be in this form, in its mixed form. I guess at this point in time, what will be most suitable for me will be that. In other words, H mu prime is necessarily equal to this, minus, here I think I would like to write it in this form, epsilon mu of x minus here, d, that should be mu, right? Yeah, mu. Epsilon mu of x. Okay, one thing I can try to do here is I'll need to raise mu. And in order to raise mu, well, the usual thing that we do, mu rho for instance, h prime rho nu equal to the same mu rho again, h rho nu minus, again, remember what I'm raising is mu. So this is unaffected, but then this becomes rho of x. And then this is going to be minus here, another mu nu, this becomes rho epsilon nu of x. Because what I'm raising is what? Is mu. The usual thing we do, at this point in time, I can simply say this is, of course, again, h prime that minus this plus that plus this. This is equal to 0.